what we are going to do in this video is to go over a review of some basic concepts in digital systems that are a prerequisite for understanding many of the concepts that we are going to be using as part of this course on mapping signal processing algorithms to architectures. As I said, this is just a review, so I will be skipping over any details but only mention those parts that I think are going to be relevant or useful from the point of view of a person who is trying to understand some of the ideas, primarily being what determines the speed of a circuit, what would determine the power consumption and possibly the area consumption of the circuit. So, the core idea of digital logic came about from the concept of what we know as Boolean logic, right. It was essentially defined as the so called laws of thought, right. George Boole had this concept where he was able to come up with a set of laws that could essentially be used to reason about the truth or falsity of statements and how do we combine such statements together. Now, the next major step in terms of as far as computers were concerned was Shannon's work on switching theory, where he was able to show that the same kind of logical operations that were involved in Boolean logic could now be used in order to understand or rather to implement certain kinds of logical operations which could potentially be implemented in terms of hardware and could be used in order to actually realize certain kinds of switching operations and computations in practice, right. An interesting side note on this, or rather an interesting coincidence over here, was also the fact that people realized we could make use of binary arithmetic, and binary arithmetic could make use of the same 0 and 1 values, whereas this used true and false values, right. In order to the binary arithmetic, in other words, could use 0 and 1 values in order to represent and manipulate numbers. Okay. So, for example, we could use something like a value 0, 1, 1, 0 could be interpreted using the place value system as 6 in the decimal system, right. And a similar extension for this allowed us to say that something like this could then be treated as minus 6 if we treated it as using the so called 2's complement system of representing negative numbers. Okay. So, this interesting coincidence, the fact that the true and false and the 0 and 1 could all be used either for reasoning about complex logical operations or for performing arithmetic, essentially allowed the development of computers. On the one hand, you could do numerical calculations by using the arithmetic portions, and on the other you could do control flow, meaning that conditional statements, comparisons, multiplexing or branching based on a certain value, all using the laws of Boolean algebra, which were originally of course defined for a different purpose, which was to understand how we think. So, as far as we are concerned, what we are going to do now is to very briefly look at the origins of digital systems, understand a little bit about the basics of gates and the kinds of operations that are implemented using Boolean algebra, but not really go into any detail. I am just going to sort of mention them and move on without really explaining how they work, because you all must be already familiar with them, right. And most importantly, we will then look at two aspects, namely timing and power, that are relevant and important from the point of view of what we are trying to do in this, of what we are trying to understand in the hardware implementation of systems. So, digital logic is built around the concept of so called gates. An example, the most sort of simple gate that you can think of would be an inverter. This is the symbol that's usually used in order to indicate an inverter. It has one input, one output, and something called a truth table that basically says x can take on two values 0 or 1, and correspondingly y would take on the values 1 and 0. In other words, if x has the value 0 on input, y would be 1, if x has 1, y would be 0. Another slightly more complex gate would be one with two inputs. So in this case it would take two inputs x and y and create output z. This of course is a AND gate. The truth table for this would be more complex for the simple reason that there are more inputs, and as x and y take on all different combinations of inputs, we can see what the output value z should look like. For the AND gate it would be 0 everywhere except when both inputs are equal to 1. Okay. Now people have reasoned a lot about this and found out how to sort of take this further. Using these kind of simple gates, how do we then build up more and more complicated systems? For example, you could use an XOR gate, could be defined as, if I have two inputs, it would be A B bar plus A bar B, which in turn would be made up something like, if A and B were my two inputs, I would take A and the inverted version of this so what I have over here is A ANDed with B bar, and this is A bar ANDed with B, and I take the two of them, OR them together and create an XOR. So this is an example where I have used simple gates, the OR gate and AND gate and the NOT gate, in order to create another gate, the XOR, right? Is XOR necessarily more complex? It depends on your point of view, it depends on which one is easier to implement to start with. But the bottom line is that you can implement some set of gates using other simpler gates. You could take this further, you could then go for modules such as a full adder. A full adder takes on multiple inputs. It would take A, B and a carry input and generate two outputs, a sum and a carry output. The sum is typically defined based on how we have done the logical operations for the addition operation, would essentially come out to be A XOR B XOR Ci, and the carry out would essentially be determined by AB plus B Ci plus A Ci. So in other words, if any two of the inputs are 1, then you can expect to see a carry out of the full adder stage, right. So this is a more complex gate for sure, because it has two outputs, three inputs, as opposed to the typical gates that have only a single output and either one or two inputs, right. I can then cascade a series of full adders together and create a multi-bit adder. Right. So I would have A0, B0, A1, B1, A2, B2, A3, B3, and I would have the sum and the final carry output over here, right. Internally there would be connections that basically cascade all the full adders together and thereby allow us to generate a 4-bit adder, for example, using basic gates. I could go further, I could then use these 4-bit adders, create 8-bit adders, 16, 32-bit adders. Using adders, make multipliers, using some other kind of logic, build up an arithmetic and logic unit. In other words, I can keep increasing the complexity at which I am building these circuits, even while keeping it purely to these kind of simple combinational gates. Why are they called combinational? Because the output is just a combination or a combinational function of all the inputs. So the other alternative is this type of gate that has a notion of so-called state or memory, right. The idea of memory is that rather than having something which depends only on the present state or present values of the inputs, is there something that can also depend on something that happened earlier, or in other words, can I control at what time or under what conditions an output is allowed to change, and then it becomes a function of whatever its inputs were. An example of this is, the simplest example is a so-called D-type flip-flop, right? So it has one input which we usually refer to as D, one output which we refer to as Q, and a separate control input which we usually refer to as the clock. So the symbol that I have drawn over here with this little triangle essentially is used to indicate that this is edge triggered. What this means, in other words, is the output Q can change only when there is a positive edge, that is a 0 to 1 transition on the clock. It does not matter what is going on the D input. And moreover, when there is a positive transition on the clock, the output is determined purely by the value of D. The clock has to have been changing from 0 to 1, so it really cannot affect the output in any other way. I can't say that it's going to be a function of the clock, because I know that the clock must have gone from 0 to 1. The output is therefore going to be determined by D. So the output value is determined by D, the time when it changes is determined by the clock. Why is this useful? Because it allows us to retain some kind of memory. I can have a single clock that is connected to multiple different flip-flops or registers that are present in my circuit, and they are only allowed to change their values at specific instants of time. Okay. This in turn can be used in order to make more complex sequential systems. The simplest example of a sequential system would essentially be some kind of a counter, which could have multiple outputs over here and might have just one single input, which is a clock. All that it does is basically generate an output x equal to x3, x2, x1, x0, a 4-bit output in this case. Every time there is a tick or a 0 to 1 transition on the clock, the counter value goes up by 1. Okay, this is one possible example over here. Note that there is only one input. So if I wanted to make this a combinational circuit where the x3, x2, x1, x0s are determined by purely as a combinational function of the input, that is the clock, this wouldn't have worked, right? What I want is there is something inside that box where I have written counter, which is keeping track of how many such ticks have been obtained over time, and is therefore able to increment them and change the output even though the input is only a single bit. Now combinational systems, combinational logic and sequential systems are combined together, and the most sort of fundamental use is to implement something called a finite state machine. Right? Finite state machines are in some sense a generalization of the idea of a counter. Effectively what they are saying is there is some set of registers, right, whose values, I am just using this to indicate that there is more than one. The values of these registers are then put through some combinational logic, where they are in turn combined with certain external inputs, and the combination of both of these basically determines what should be the next set of values going into these registers, right. So there is a clock that determines when the state of the system is allowed to change, and there is a combinational logic that determines the functionality, what is being done as a combination of the state as well as the present set of inputs, right. The most interesting sort of generalization of this idea of a finite state machine is to take it forward into something else called a programmable finite state machine. The idea over here is the transitions or the next state logic, right, can be stored in some kind of memory elements themselves, right. So rather than saying that any time the present state is this and if the input is this, then the next state should be this, rather than implementing a combinational logic that does that, what if I made that, replace that combinational logic with something which could be changed dynamically at any time that I wanted. In other words, I put a block of memory there, a lookup table so to say, and if I can dynamically change that lookup table, I can basically change the behavior of the state machine with time. This is the core idea of a processor, right? The fact that the combinational logic or the behavior can be changed at any time by reprogramming the behavior of the next state logic. Of course, that's an oversimplification, but it sort of captures the core idea. That idea that you can change the behavior by changing the next state logic is what is the basis of a processing unit, a processor, a CPU. So now as far as we are concerned, we are not going to be directly implementing programmable FSMs or CPUs, but on the other hand, as we will see later when we actually get down to implementing certain kinds of hardware accelerators, the finite state machine idea is a core concept that is very useful in all of those, right. Now as far as we are concerned, the most important thing that we need to keep track over here is how do these combinational and sequential logic gates get implemented, right. Most of you would have done a course on CMOS digital systems, CMOS based digital systems, hopefully on CMOS VLSI. I am just briefly sort of going to review why they are used and how they end up getting used, right. The idea that we have over here is that, for example, let us say that we are trying to implement AND logic, right. What we have over here is there are two inputs, A and B, and they need to get translated into an output Y. Effectively what we are saying is, if A is 1 or if A is high and at the same time B is also high, then the output Y should also be high. One way of representing this in terms of switches that you might already be familiar with is to say, I will consider a logic high over here, have one switch which is connected to A, another switch that is connected to B, and over here I will essentially look at this as the output Y. If A is true or 1 or high, the switch is closed. So what would that mean if both A and B are high? It would mean that the output Y would be true or 1 or high if both A and B are true or 1 or high. Okay. That is the sort of core logic that we are going to be implementing as far as this using these switches. Okay. But how do I implement such a switch? That is where the concept of the transistor comes in, and in particular the CMOS based switches, right. It turns out that the transistor, although it was originally sort of designed for the purpose of amplifying analog signals, could also be used in order to implement this kind of digital logic. It could act as a switch. How do we use that? The core idea, once again, you are probably familiar with. This is what the simplest CMOS circuit looks like. We have a high voltage over here, ground over here, the input over here, and the output over here. How does it behave? when x goes towards VDD, y goes towards 0. Why does that happen? Because when x is high, this goes off, this is on, and this gets pulled low, right, meaning that there is now a conducting path from y to ground, which is equivalent to basically saying that the output has been connected to the ground terminal, and therefore the potential there would be pulled down to 0. Instead, if we had this going low, then what we would have is this would be off, this would be on, and the output would then go in exactly the opposite direction, because then there would be a current path pulling the output upwards to VDD.